Hi, this is our presentation on our project called Speedy Motion Detection. I'm Charles.
And I'm Sushma. So let's look at the motivation of our project. The first thing that came to our mind was like children's safety. When objects are falling or moving at a fast speed, like it can be dangerous for kids. So we want to send an alert to the parents. And also when an elderly person falls in the household, um, we can send an alert to their family. This is also very useful in places where which are very earthquake prone, and it's also useful where at construction sites. Problem description. We're using a one-point perspective camera view. We're using random objects of different sizes, shapes, and colors. We're also having objects which are initially present in the frame and objects which are later come into the view. We're having objects which are falling simultaneously, with the exception that identical objects cannot be tracked when they're falling simultaneously. Also, we're only detecting the objects which are falling with above a certain threshold of speed.
Okay, so here are some of our design specifications. We want our implementation to be really fast because we want this to work in real time. It should be versatile, so we should not need to have any knowledge of what type of object is falling or moving in the video. It should be robust, so it should work with any kind of camera, no matter whether it has really low resolution or frames per second. Also, it should be intuitive. We're trying to use as minimal of functions from black box libraries as possible, so that we have a full understanding of the issues that arise. For example, if an object is not being detected in one of the frames, we know exactly what's going on. And lastly, we want it to be completely transparent, so everything in the process of our algorithm is visualizable, starting like from the motion mass to the IDing of the objects themselves, and lastly, most importantly, the bounding box around the objects that we deem are speedy. So here is our design and implementation. This is an overview of the whole process we take. There are 4 steps to this. The very first one is motion masking, where we are thresholding differences of pixel values between different frames. The next step we take is connected component labeling, where we retrieve the objects and their shapes and sizes. So we just get like an object for every, say, clump of pixels that we say it's distinct from the background. The next thing we do is object identification and tracking. So we determine the similarities between objects in different frames and track their positions over time. Lastly, we use a speed filter by calculating the speed of the objects and selecting the objects that are above a certain threshold to appear in the final video.
So as Charles just said, the first step we perform is motion masking. In a static reference, we compare frames with an initial frame and an end frame. And what we obtain is the object at the current frame, and also the object which is absent in the current frame but which was present in the initial frame. In a dynamic reference, we compare the current frame with the previous frame, and we get a lingering effect where the detected object, the detection is a little larger than the actual size of the object. So like the dynamic reference is not necessarily bad, but it's not ideal. So what we do is we do a union of the static frame reference and the dynamic reference. So we did not obtain nice bounding boxes. What we actually or like a single bounding box for the object. What we get are like these tiny boxes with holes. So we perform morphological operations on the mask that we obtain from both the static reference and the dynamic reference, and so that we get a filled up detection with and a detection where we get the complete object. Now the question arises, do we want to perform these morphological operations even after the union? The disadvantage of that is that when two objects are moving pretty close to each other, they can be detected as one object, and also very small objects can be completely ignored. The next step that we perform is connected component labeling, where different objects are given different labels. But we do not want to deal with pixels because they're very complicated. So what we want is bounding boxes with XY coordinates and a width and a height of the bounding box. Now the challenge that arises is when in different frames, the same object can be given a different label. So how to track the same objects over frames?
So this is our solution to that problem, object identification. We assign every object in each frame a score. If the score of the object is similar enough between frames, then we can say they are the same object. The way we assign scores right now is very rudimentary. We break it into the color HSV color space. We average all the pixels within that object, multiply it by certain weights, and sum all of them together to get a final score or ID for the object. Those weights we sort of tune by ourselves. Those are things that we adjust through trial and error just to see if we increase a certain weight, whether that improves or makes the result worse. So one of the issues that arise was that we were capturing some of the background when we were doing the averaging because the object is not completely doesn't fill up exactly the entire bounding box. So our solution to this was to weight the pixels in the center of the object more than the pixels on the outside. Okay, so determining similarity between objects. So we implemented a quantization by just rounding, like say, to the nearest 0.05. This results in pretty good results. For like the green box over here, both of them round to 0.45, which is good. That means it says they're the same object. However, part of the issue that could arise is that if our quantization is too small, then say for the purple box, 0.63 rounds up, 0.61 rounds down, and they're detected as different objects, which they are not. So this could be a reason why during some of the frames, the object is not detected. And the way we sort of keep track of the trajectory of the object is to store them in a dictionary, where the key is the score of the object and the value is a list of the object's data. The object's data would include the time step, or the time and the position at that time. Every time a object would have the same score, it would be appended to a list with the new time and the new position. Anytime a object would have a new score, then it would there would be a new key value pair added to that dictionary. A necessary assumption that we had to make was due to the fact that we were getting objects with the same score in the same frame. This is an illogical failure because this implies that the same object is in two places at one time, which is not possible. The way we dealt with this problem was to just ignore one of them, and this was done arbitrarily. So the last step of the entire algorithm was just to do the speed filter every time a new there was a object with the same score in the dictionary. We were able to calculate the difference in the position and the difference in the time, hence the velocity, and we can check whether that velocity is greater than the threshold. And if it is, then we say it is speedy.
So let's look at our results that we got from our project. So you can see we're using random objects with different color, shapes, and sizes, and only the objects that are moving fast enough are being tracked as falling. And if you notice, the big objects like the white box or the brown stuffed toy has a shadow, and even that is being tracked. And also, like there are objects that are present in the frame from before and are stationary, and then are getting tracked only when they're moving. So in this video, we have two objects falling simultaneously, and both of them get tracked.
So in this last demo, we have just one object falling, just a standard object. And then we have also a object or a backpack that comes into frame that's not moving exactly at the necessary speed. So it's not being highlighted until the end where it says it's falling. So some of the improvements that we can make to our project. The first thing is we saw a lot of the shadows being tracked as part of the objects. And we can potentially do some thresholding before we process the video so that we can have a mask that excludes the shadow, and hence only the object is being tracked and not its shadow. The second thing we could do is edge detection. So when we're drawing bounding boxes around it and determining a score for the object, we're simply just taking all those pixels in that box and using that, and that includes some of the background. So if we had a way to define the contour of the shape, then we can just use the pixels of the object itself to determine that score. And lastly, for determining object similarities or scores, we can implement a machine learning algorithm so that we can move away from manually adjusting the weights ourselves and having the computer just like choose the weights once we feed it a lot of images of similar objects and different objects. We can also adjust the object attributes. We're just using say the average HSV values, but we can also use, say, the straightness of the contours or like various other things to see whether objects are the same or different.
And thank you for listening. So you guys can reach out to us if y'all have any questions, and we have our email IDs provided below.
All right, thank you.